Right. We'll do this in class today. Had some interruptions, and so I'm gonna make a little condensed version of what we're gonna do today. And, what we did earlier in the day, which was, and doing some stuff here. Just quick. So the new assignment for the next part of the screw conveyor is just the screw, the auger, parts assembly and drawing. So we're going to jump in and develop that. And so what we looked at was back to our manual, Siemens manual. Well, following the Siemens standards in this manual. That is under here, right? This is what I got there. Yes. So I need that open. I've got it open. I'm just going to cruise through here and look at some of the screw stuff. I explained a lot in class that I won't go over today, but or in this video as I remake this. But yeah, I'm just building a screw here. Goes in my housing. So if I cruise down through here, they have a few particulars about it. Um, got all these components. I'm gonna go down below the materials guide, and I think we go into how it carries, and then into the design data for the screw. I just briefly mentioned in class that we can do left hand or right hand screws, just kind of like a fastener, and right hand being the most common and what I'll use unless there's a good reason to do a left hand screw. But in our case, we're gonna do a right hand. Depending on which way we rotate our shaft, and depending on which end our drive is, will make the difference in how the product conveys down through here. So we are actually doing what I didn't point out in class. If I look at all these different configurations, they're calling it the hand of the conveyor, the handedness, right or left hand. We're going to do a right hand screw flights. We're going to drive from like our discharge in. And so really, and our product is, this is showing you where the product would go. If I turn my conveyor, essentially that's clockwise as I was looking at the discharge in, it would actually pull this material through our housing towards. And all I have to do is switch the rotation to actually push the other direction. And in left hand, it's probably just the opposite. If I was left hand flights and I was spinning counterclockwise, I would be pulling material towards me. So yeah, there's reasons why I would design whichever one. The other thing we talked about in class a little bit is how do I even identify those? They are actually hard to notice if you just look at a screw. It can be kind of hard to identify. Is it left or right? How they usually identify it is come to the end like this, where you get a flight cut, and the ends where the flight starts. You'd actually kind of sight, like almost put yourself in this position of this view, and a right hand will look like it goes down and to your right as it then comes back up and around and then down and to the right. So the left hand is just opposite. If you look at the end, it'll go down and to the left. And so it really matters. Um, so I have the option of both. And so what we did is just looked at some of the dimensions I might need. Let me come down here. We are kind of doing a helicoid conveyor screw, but we're doing them in sections instead of just a continuous screw flight. We are going to do ours like a section by section. So I think it's the next, it looks just like this, but, and I think it's similarly broken down variable wise here. So yeah, maybe sectional flight head screws. This is probably the most pertinent information. I don't think some of the data we have here is probably the same in those other flight designs. But let me go down to a picture here and see if this has a sectional conveyor flight screw picture right here. Each flight is blanked from a steel plate. That's what we're going to do. So what we have is, if we just look at the parameters around a screw conveyor, I need to know the overall length. I need to know what we call the pitch, which is like a thread on a fastener from kind of peak to peak here of our flights. Each one of these is called a flight, or these are called the flights. This would be called the center pipe or center shaft. So I need to know that diameter. and I need to know the diameter of the screw, which is really this is kind of the driver of all of our engineering information. We were designing around a 10-inch screw, and that is the outside diameter of these flights after they're impressed here. And so we have a 10-inch screw. We have an 11-inch housing. It's an inch difference. I mean, there's a half inch all the way around it, and that just helps if I have warpage in my screw. If it's kind of if it sags a little bit from bearing to bearing, I won't rub my housing. And for some products, um, we have to really consider how tight our screws are to the housing versus this one. I'm kind of designing by a general standard of just following their manual, and so I have that full half inch of clearance around my shoe. So and I need to know the overall length. So a pitch length and diameter of screw. So a pitch, and if you were to spend time reading through some of this data, um, like a standard screw pitch is going to match its diameter. So if I have a 10-inch diameter screw, kind of a standard normal would be like a full pitch, and that would be a 10-inch pitch. And those would be your most common types of augers, unless I have reasons to have a tighter pitch. And generally beyond pitch um, greater than its diameter, I think is very uncommon. I think it's most common to have pitch match diameter, and then it's also common for other reasons to have one that was less than a full pitch from flight to flight. And what I said in class was that the when that comes when I think of that, it may be inclined. Ours is going to be in the horizontal position, the screw conveyor in its assembly. And if I did have a vertical auger, which means it maybe goes from a low elevation to a high elevation, they use screw augers to do that. They can even put one straight up vertical, up and down. And sometimes they'll do 2/3 pitch, or even half pitch, so pretty tight when they have those vertical transitions. Um, even a vertical transition is slightly on an angle, and going from a lower elevation up at an angle to a higher elevation. Sometimes they will, and I think the design around it can drive when you would tighten up the pitch of a screw conveyor. So I won't go into super details of that, but it does happen, and they have some examples in our manual here. I'm going to do a full pitch. So I already know a couple of my dimensions. I know the diameter is 10-inch. I know that my pitch is 10-inch, and I just need my overall length. And then maybe this diameter here, but I think I'm going to put this up in their chart here. So beyond here, this might be the same redundant information. This is just sectional flight. It's like this chart or the chart above this. I think I could use either one. I don't think I get conflicting data with it, but I've marked up both. Just a quick peruse through. This is kind of what we're gonna make here is these flights that look like this helicoid shape. So Inventor has some processes to make that kind of easy. Um, and then down in here, I won't go into too deep, but they do have different reasons with making different types of flights. Something that wouldn't, maybe a material that would be prone to pack into the flights. Maybe this allows it to not pack. It breaks away from the center pipe, the flight from the center pipe. And I think if we read through this, we can see what their design intent was. And then we have a bunch of different other ones here. Short pitch, usually short pitch, incline conveyor right there. Okay, so that's good reading for just general information. One that was also common to see in my industry was a mixing paddle style. So not only is it going to convey the material, but we're actually going to get it to flop. And I think the example I use is equipment that makes hash browns and tater tots, like this forming equipment, Play-Doh former ones, swishes it through there. They'll bring in a product that's ready, cooked and ready to form. And then ahead of that, they may have some seasonings or some dry ingredients that come in before pressing into the shapes, like the tater tot shape or hash brown shape. And so that ahead of that equipment, it was a mixing conveyor, mixing conveyor, and it will have to be designed to mix with the amount, have to have it long enough to mix my product right. So I'd be dumping in my cooked potato product, if, cut and to shape that it needs. And maybe at that same point, it's dumping in some seasoning. And then as it augers that thing, off that material to the forming equipment, it's going to mix it along the way and give enough time to mix before it gets pressed into the form. So that's another common one that I've seen with a mixing paddle type conveyor. Anyway, we did talk about those over class. Now let's just go on to the design and consider what we might need. So what I need to know, I need to know that pipe diameter. That's probably the last thing, and really my overall way. So the pipe diameter is going to be driven by this chart here. So long as a 10-inch screw tells me my pipe size is going to be 2-inch. These are, and these are not. So this doesn't really point to like which. It has these variables, but I was looking to see on the top column that they identify their variables. They really don't. I don't think this one does either. Yeah. This could be, I think it's pretty close on this one here. I think this one does have the variables. A is the diameter. Yeah, I'm just here's this. I think this is the chart I pulled out. 10-inch. I have 3 different options for 10-inch diameter. 2 of them have 2-inch pipe. 1 of them has a 2.5-inch pipe. And that is the center pipe of quads. And my flights will go on that. I'm going to use the 2-inch size. They give me just, you wouldn't know. I mean, this is a nominal size value from the pipe world. We don't know the OD or the ID of the pipe, and that's driven by schedule, a pipe schedule chart. They give it to us here that the OD at least is 2 3/8. And then the gauge of my flight is going to be 10 gauge. And the pitch is 10. So I could use heavier flights 3/16 with my same center pipe size. If I go up to this pipe size, I'm going to be using 3/16 flights. So I'm going to stay on the slider end of this, but there is an argument that I am moving for potato and maybe 3/16 would be a better selection. I'm going to stick with 10. So 2 3/8 on the OD and a 2-inch pipe. So what I'm going to do is, what we did is we developed the center pipe first. And there's another variable chart in here. I think it's closer to the end drive shafts. Let me see. Yeah, I think it is. I think it's down here just a little bit below the flight information. Then it goes into maybe bolted connections. We don't have to do this, which is because they are a little more complicated, bolt end to end. Actually put a hanger bearing in between. This is the other chart that I want to refer to here. Only because I want to know, like we have our housing built end plate to end plate. I need to make sure that I'm everything's going to fit inside there in my center pipe. They're going to give me some specific dimensions here. So whether it's the drive end here with the this is what this is, a drive end shaft. I can tell it has this keyway look here. This is designed to go a gearbox to go on this or some kind of gear. And then this is what we call the driven end. It just has a bearing. So the bearing is notated by this little X pattern in this view. It's the bearing area of the shaft where it's going to seat against the bearing. And so, and this, although they give me some variables, really what's going to drive some of these lengths is really the bearing selection that I've made and any additional components that I'm putting on between the end plate and the bearing, which we will put a seal plate between the two. And then, so some of these are going to change, but I'm going to go with them as kind of a guide. When I design my shafts and I design my center pipe, and the way that this was, we talked about how it's a pipe that's holding all my flights and it's hollow. And then the way we make that transition to something that I can drive and put a gearbox on, we use a solid bar for this. So it's a solid round stop. And it drastically reduces weight. That's good. If I use the solid bar all the way across, for one, it's a lot of material. The other, it's heavy and maybe it's prone to sag even more. But there are some reasons why I would use a solid center. But maybe in a really heavy duty application, and then in an application that I've accounted for how much sag that's going to have, as it spans from bearing to bearing. And so Mine is going to be a hollow pipe, and it's going to come in this E dimension is what I paid attention to. They really give it as kind of from the outside of the end plate to the end of the center shaft, either on the drive end or the drive end or driven end. And so I think the E dimension might be the same on both of these. They kind of have a broke down, and I call this driven end and drive shafts. So E dimensions 1 1/4, E dimensions 1 1/4. So technically, and my end plates are 1/4 inch thick material. So this is going to be 1 inch from the inside of my housing to the center pipe. And so that's going to become up one of those lengths that I need to know. And I can use my housing as the dimension to pull. So let's go here. So if I just kind of go up here just real quick, I think that kind of look at it's going to help me take care of these other ones. I'm not going to pay too much attention to here. We can get into particulars and maybe what's going on here as we develop out our shafts. But so like nice little, I guess here. So what I've determined is I know this, and I'm going to go determine what this is and make that something. So I'm going to go over to Venture and open up that new part. Just make a standard part. This is not sheet metal, so standard part. You design it front in mind. Here's my front view. So I'm going to draw this in the front. So let's do some sketch. Front plane, it's max Y plane. What we need to draw is I'm just going to draw the profile of the center pipe, and then extrude it out how long I need. And let me finish that in just a second. I'm going to go in and open that my conveyor. My housing. Assemblies. Here's our housing that we built. I'm just going to go and open it up just to use as a reference real quick. Need to know the inside measurement, right? So I need to know the inside of end plate, inside of end plate. It is 96 inches, 8 feet. So according to that little chart, I'm going to come in 1.25 inches from the outside on both ends, and that's how long this is. So I'm essentially going to come in from the inside, an inch on each end, 94 inches is what I'm going to extrude this to. And then the last thing I'm going to check is just type schedule chart. And I didn't load one in here. I still need to load it, but it's a link to one that I like, which is it's USA Industries. I think I have the link in the theory class, and I'll bring it to the app. USA Industries pipe schedule chart. You type that in. It's one that comes up pretty soon. I don't use that one. I use this USA Industries one, their distributor of steel. I just like it because it's really simple to use. Just clear this selection. It's 2 that I have. Maybe looking for it. Reset. There we go. Normally you come in like this. We're looking for a nominal pipe size of 2 inches. So I will enter that, and then it gives me that OD that we saw on our chart, 2 3/8. 2-inch nominal pipe size, 2 3/8 OD. The ID depends on the schedule, how thick it is. I'm gonna use standard schedule for 40 ID. So my ID is 2.067. So I'm going to go back and use these 2 values to draw this 94-inch piece of pipe here. So I'm going to do I've got a schedule start on this right plane. I'm going to go ahead and I'm going to lock into the center here so we can string. So 275. Outside diameter of 2-inch pipe. 2.067 inside that. That's something that we can look at. 2.06. That's the profile of the pipe. It's finished. In the front view, I'm going to extrude that back. I'll just extrude this over 7, I think. So you say extrude that profile. Well, I'm going to go both ways of here. And my overall is going to be 94 inches and take the end plate on the inside. Inch to spare on each end. Say okay. I'm gonna go ahead and make this stainless. We need stainless steel, semi-polished, I'll leave it like that. I think in class, we just went ahead and updated the eye properties while I was in the part, especially the description that shows up on the parts list. So I'll just say this is 2-inch. Skin, and you put stainless steel, 2-inch schedule, yeah, I put stainless steel, let's see, but that's all. I can even leave off pipe. This is understandable too. I'm taking stainless steel schedule. A simple description. Let me save this part. I think even put them in assembly, I think you have to save them. So I'm just going to go ahead and save kind of a redundant one for me. I think today we made 17 and 18. I'm just gonna do a quick little check. I'm gonna make a duplicate of ours since I'm remaking my video. So we just shut. I'm just gonna shut it. 16 was the pipe we made, 17 was the flight we made, and I made an end shaft toward the end points. 16, 17, 18 are what we created today in class. We'll go ahead and use those same numbers and natural part here. So let me say that. It doesn't matter what you're looking at. I'm just going to dash something that I can see it. Dash one. So we can move these to an obsolete folder. I'm not going to just do them for my video. All right. So that part, so I've got it saved. Now I'm going to open up another part. I'll make the flight. So I'm making these two parts kind of separate from each other. It is a sheet metal part for these set. Scrape that. I'm just going to go ahead and load the defaults in this. It's 10 gauge. And so these next two things are going to come into play. I've already got my length taken care of, my center pipe length. So I need to know that's 10, that's going to be 10, but I need to know the thickness of that flight. It's 10 as well. But where I was pulling that up from is down in either of these. It's 10 gauge, or I could have done 3/16. I'm going to do 10 gauge. What is that? Well, I have there is in this thing a sheet metal pH chart towards the end, or I have this one loaded in my resources, this sheet metal gauge chart, resources. So I think they're the same. I think I've checked them both for the same value. So 10 gauge on here. 10 gauge is, depending on the material, I got stainless in my first column. So 10 gauge 0.1406 inches thick. So I'm gonna set my sheet metal defaults with this one. So I'll do that right now. Sheet metal defaults. I'm gonna establish a new rule. So we new call it. 10 gauge stainless steel. 10 gauge. 10 gauge. Oh, there's my name. Just need to define. Let me go to it. And it is stainless. And it is that thickness. The thing we've been doing on here is I've gotten rid of this A dimension in case I ever do kind of a flange relationship. I've just been putting 30 thousandths. And on the corner, I've been switching to tear instead of. So save and close that. Make sure that's the one that's loaded. And now I've got that set up. I'm ready to design this part, which is the flight. So there's definitely multiple ways I can do this. So what I'm going to do is I'm going to use a 3D sketch to do this. So I'm going to turn on these planes. I don't always do this if I've got my bearings, but I'm going to keep track of myself here. I'm looking at my view cube. This is front view. I'm going to have my flight go down my shaft that way. So I'm just going to design this. So what I'm going to do is I'm going to say, instead of a 2D sketch, let's go ahead and pick 3D sketch up here. Start a 3D sketch. And it just jumps to going. And because I can draw on any of these three planes, it gets a little confusing here. It's not like I'm defining a plane and doing a 2D sketch. I'm like, I have quite a bit of liberty here. And so this is confusing. And so it's good to get at least some exposure to it right now. It is a handy way to sketch an inventor. works well for this. So they have a helical curve command in this 3D sketch world because the ribbon menu is completely different actually. Constraints are a little bit different. The way I project what I'm able to project is a little bit different. So I'm gonna start with a helical curve. I actually already have kind of I've got a hold of it. It's like it looks like this. It's really confusing. But what I'm going to do is just place it anywhere, and I'm going to build mine so that it's like my shaft was built, from front to back, kind of along the Z-axis. Is what that blue axis is, right? And so I'm gonna build this thing so it's constrained to the Z-axis. So I mean, I can come in here and just like lock it. I really don't think I'm locking it on here. I probably could put this anywhere and just click. And then it's the next thing it wants to know is, what is the next axis that you're gonna build this helical curve. And I'm gonna choose to do the Z-axis. It's blue one that pops up. It really wants to jump to one or the other of these, right? It wants to build things kind of perpendicular 90 degrees. So I'm going to snap it here, even though it's really not constrained to it. I'm kind of letting this UCS kind of project the way I'm going. There it is. I can even see it as I go longer here, building a helical curve around that axis. So I'm just going to click out here, and then it wants to go to right to diameter. I can actually move over to this dialog box and start inputting some data. And so I'll do that. It's still not constrained, but what we're going to do is we're going to say, I'm going to do this, what do we got here? This one, I'm going to do constant helical curve, where I'd have a variable. I'm going to use constant, and then this is my rotation, left hand and right hand. Looks like my default loaded right hand. I'm going to make sure that's selected. And then I have options in how I want to define this helical curve. So I'm going to use pitch and revolution though. And find the diameter. Ours is a 10-inch auger, so I'm going to say it's 10 inch. That thing kind of jumps to that size now. It's 10-inch diameter now. The pitch, I also need to be 10-inch. It's kind of from the start to the stop. It's one full pitch. That's what it's going to kind of look like. I'm doing sectional flights. And then the revolution, I just want one full revolution. One full. And then I would have multiple of these like welded together to make my whole setup. So I'm just making one full pitch flight, and then I will just make, and then I'll see how many I need to go all the way down my center pipe from inlet to this trim. So I think that's all I have to do is say that. Those are my parameters there, and I say okay, and then it just throws it in there. It's just not constrained at all. So I want to constrain it somewhere in model space. So I am going to constrain. I'm going to use a coincident constraint. I'm going to say to this endpoint here that's on front endpoint, and I'm going to put it to the center point. So I'm actually selecting it from over here. I've expanded my origin tab, and there's my center point, my center origin. So I've constrained that point to point. And then it still will allow it to tip. Even though I drew it on the Z-axis, it allows it to kind of tip off the Z-axis. So I'm going to use this constraint that is parallel to Z-axis. So like I said, the constraint selection is different here. So I'm going to use this one, and I'm going to constrain this to the Z-axis. And now it does, at least the axis of this is constrained. Kind of its reference material. And then what we need to do is it just doesn't know where. So if I can actually spin this thing, that I'm just kind of like turning it, almost like I'm pulling. I almost like click on it and pull it down. So what I'm looking to do is like define where these endpoints start and stop. And I'm going to use an origin plane for that. So I'm going to say, just to make constraining this easy, but what it needs to know is where in space is that point locked down. And so I'm going to say it's going to lock down to this plane. And I'm going to call that plane, like that location, 12 o'clock. So I'm not going to try, I'm going to be strategic here. Kind of, and when you're applying constraints, which is what I'm going to do here, another coincident constraint, sometimes it helps to move the things into the close to the position you want them to go. If I still have that rotated down here somewhere, and I do a coincident constraint from the endpoint to this plane, it might snap it into the 6 o'clock position, which isn't the end of the world at all. It's just I'm just paying attention. I'm trying to kind of control this a little bit, and because I have to make 2 of these helicoid curves to make this is just the outer diameter as it spirals around. And so what I'm going to do is I'm going to constrain the coincident constraint this endpoint to this plane, which I've turned on, which is the YZ thing. And that's all it takes to constrain this thing. So it's that one dimension, then a couple of constraints, a few of them, and we are locked in model space. So that's one. And where this lives here is I'm in this 3D sketch, but now I've actually kind of got a subcategory. This is the helical curve. So if I ever want to edit that again, I'd have to come in here and edit the helical curve, and I get that dialog box to show up. I can totally make any adjustments that I made in this calculated. You have to go into the sketch and then go into this. So it's just kind of another subcategory of your sketch. I'm gonna do one more helical curve. Helical curve. And sure, I'm just gonna put it anywhere, and then I'll define where it goes. But I actually I think even the UCS is hooked to the end of my line here. I think there is a point to grip on here now. I'm snapping to the end point of that constrained reference line for the first helical curve. But I want it to be also be on the z-axis like this, and so I can just snap it there. Any length really. Just I'm going to define that with the dialog chart. So I'm just looking to click here, and we can just jump over here now and say, well, this diameter is the inside of the, it actually is the center pipe OD diameter. So I actually have this section removed because I have a center pipe running down the length of my screw here. So and that diameter is the OD of the center pipe, which is 2.375 in my charts. I'm just going to give myself a little clearance. So this isn't size on size. I'm going to bump this out to 30 thousandths. So I'm going to say, I'm going to add, it's going to be, oh, sorry, plus 0.030, that's 30 thousandths. So this is going to be my dimension. And I talk about this in class quite a bit. When I add these like tolerances into my parts, I generally like to express the dimension as an equation like this. And that way I can see the OD that I selected and how much clearance I had on it. It's been pretty common. I've sketched this way in a lot of my data inputs. And that's just so I don't see some oddball number that I really don't even know what it is. I can see what I've built in here. So I've talked about that quite a bit. It is my technique to see when I built tolerances into parts. It also is a 10-inch pitch. It's going to span the same distance. It's a 10-inch pitch. I just need one revolution. It's going to terminate. That'll make it terminate kind of the same input. It's a different diameter, but it really is a 10-inch pitch terminating like that. And what this is weird. You can't quite identify it yet, but I'll show you what we're going to do. So I'm going to say okay, and I'm going to do some constraints on it. So this is all my parameters. Okay. And now I just need to do similar constraints. Like it isn't locked in on the z-axis. So I'm going to make that a parallel to the z-axis here. You can go ahead and constrain its center line. And then I just need to constrain its endpoints where it starts and stops. But I want them to start and stop the same plane. So they're perfectly in line here. That's actually what we mean. Right? I can see that's where my center shaft hits down through here. And that's kind of what it would look like at the end of an auger when I'm looking at it. However, this is actually what's going to twist. So let's do this. Let's pull this around. And moving things in 3D space is a bit odd for sure. So if I just pull this just a little further. Yeah, so now I'm close to my plane. I'm just going to do a coincident constraint some way. I'm going to do that endpoint to this YZ plane, and there it is constrained. So we tried a few ways in class, and because originally I came in here and I said I'm going to put a line here, and I'm actually going to build like a closed polygon. This turned out to work just fine, like functionally looking like it was. So I've just locked those two together. And then I'm going to do another line. I'm going to snap it to here. And so that is actually, like, you can kind of visualize that is what that part, that's the shape that part is going to make. What we found out is the original way I did it, I wasn't able to get a flat pattern out of it. And then in class, Riley was like, well, I did mine a little different way and it worked. And I was like, perfect, I'm gonna do that too. It's just a slight adjustment, it almost looked the same, but it actually did allow the flat pattern function. So what we had to do is like not do a closed polygon, but we just used a loft command, which is the first time we use that too. So I just ended up turning these to construction materials here. So I needed them for the way I originally planned to do it, and then I didn't end up needing them for a loft. And so this was the end of my sketch. And if I just say finish this, that is my sketch. I'll turn off my visual planes here. Because now I can kind of get my bearings. I can see myself in 3D space. But what we're going to do is we're going to do a loft, or yeah, you have a couple ways to do it. On a sheet metal part, I can do a lofted flange, but that's not what I'm going to use for this particular application. I'm going to use the 3D model tab, and then it has a loft right here. It also has a coil and a sweep, which I don't even know if we've experimented with these yet. So these ones kind of drive similar, but I'm going to use this loft command because it worked for us. I'll be able to kind of tell what it's doing is I pick a shape and then pick another shape and pick a path for it to go to. It does take two or more sketches to do this. You can't do this in a single sketch. And really, I have a sketch with separate elements, so it allows this to work. And so if I choose this loft command, it just wants me to choose, I kind of have outputting a surface, is not a solid. And oh man, this is a pretty detailed little box here, but I'm gonna stay in this first curve section. It just wants me to choose what I'm lofting. And so I'm gonna say, I think from in the sections area, am I getting that right? Yeah, there we go. Sorry, just looking at the selection. I want that sketch and that sketch. And it already starts to produce what I'm looking for. I'm looking to build a surface. Those are kind of the boundaries of my surface there, like that. I get that witness. That's what it's going to look like. I don't think I have to. I don't think I'm changing anything else here. There is a lot more functionality here to explore, but this is going to work for me. I'm going to say okay, and it's kind of built this surface, consume my sketch, and built this surface of a part. And now I'm going to thicken this. So on the same 3D model tab, thicken. I've already set my sheet metal defaults. I think it recognizes the surface as a face, yes. And then it starts to build the part for me. It's a good sign if I'm getting all these witness things to show up as I'm selecting. If I'm not, I definitely have some issues with sketching and so I'm going to straddle this both ways. I'm going to call that my center plane through the part that we've defined so far. And then I'm going to say this is thickness. Has to be written in this uppercase first, lowercase rest of the letters to use that parameter thickness. It's a solid. Okay, so I'm gonna say, yeah, that is one flight, 10-inch in diameter, 2 3/8 plus a little tolerance on the ID diameter, and it spans 10 inches this way. So this is a way to make a flight. I bet there's several different ways to do it as well. And then I just would check on the sheet metal tab if I could make a flat pattern. This one, to me, the A side is less. It's really inside a piece of equipment, and both sides get beat up in an auger for the most part. So to me, it wouldn't really matter which side I choose. I'll still choose a side just so it is defined which side is A side. I just chose that side. And then I'm going to say create a flat pattern. There it is. There's the flat pattern. That's a good one. This is how we have to actually cut that to make that shape. Cut this flat, and then there's equipment that makes these parts. Like some companies you don't even have to do this for if they have pretty new equipment and they have like a flight pressing machine. Generally those come with software that all you have to do is have a local note on your drawing. Like I need a digital a digital replication, representation of the part especially in the assembly. And that might be sufficient for people with newer equipment, companies with newer equipment, and they have a flight press. And so I can build my part so that it works in my assembly. It doesn't really have to be the most functioning flat pattern part because they're gonna use the equipment software to develop flat patterns for themselves. So all they would need for me to tell them on my print is just that these are like with a leader line on my print when I'm pointing to these flights and say that these are I would just need to have a local note that said all the information that it's a 10-inch diameter. I could either tell them in my local note that it goes around 2-inch pipe and let them have to do the figuring, or I could say it's 2 3/8 OD pipe for the center pipe, and then it's 10 gauge, and then it's a 10-inch pitch. So it's 10-inch auger, or I could even say standard pitch, and they would know that if they knew flights. But 10-inch and 10-inch diameter what the center pipe ID diameter is. And they may not need you to even figure out any tolerance. The program may already have that. So you could actually design that right to the pipe actually in the model. But it would just depend on what equipment you're feeding essentially as a designer. Um, Anything else I would say on that? Yeah. So our drawings can be both ways, depending on what we have access to for manufacturing. Flight press, or these can actually be even roll formed. It is kind of like a cone that it makes, or they would be press formed. Um, and some places will make their own dies that press form. So there's just a lot of different ways people make this with what equipment they have. And so, being able to produce a flat pattern is very helpful. Um, Maybe in some companies it's not necessary. Just give them the information they need to define and the equipment to make the flat pattern. So it depends. But I like having flat patterns. That's good for what we're doing. And I'm just going to go ahead and save this part. I'm just going to turn off this lofted surface real quick. And so this part is just pretty simple. Go ahead and save that one. That was the next one I made, which is this one. So -1, save. So I've got that part. I've got the center pipe. We can go to an assembly now. So the next thing we did was we went to an assembly. I'm gonna check my assemblies really quick. I think it's just 1 and 2, but I'm just gonna verify that. So number 1, yep, was when I built my, and 2 is when I put them both together. So let's make a new assembly. English standard assembly. I'm gonna go ahead and place in my center pipe. So I'm just gonna come to my placing in parts. The one we just made is this one for me. So I'm gonna place that in here. There it is. I just need one of those. I'm gonna ground and root this thing. So I'm gonna pick ground and root and put this, and I'll build it off of it essentially. So I'll say, okay, ground and rooted front to right side. I like it. Yeah, it's front is front. I probably made a mistake in class actually a little bit. It still works, but it's okay. Here we go. So, and then I need to put in my flight that I created. So let me grab one of those. It's this one here. Put this in. I'm just gonna place one. Then we'll pattern this thing. I just want to constrain this to this. Oh, I talked a lot in class. So I do like to use the origin for the assembly planes and axes, especially here where I have things lined up with that, ground and rooted to that. And then I'm going to open up my actual part origin here. So I get to its like the origin axes and planes on the part itself. I'm gonna use these to constrain it for the most part. Uh, these elements here. So the first thing I'm going to do is I'm going to move this over onto the Z axis because it has its Z axis down the linear length like that. So I'm going to align it to the Z axis of the assembly, which is also where the pipe is ground and rooted to. So the first thing I'm going to do is constrain Z axis part to Z axis in the assembly and just slaps together like that. Um, yeah, I might, and I'm going to make one adjustment here. Um, because I can already recognize it. If I'm thinking of the orientation, this fits into the housing, and I know that my housing is front is discharge, back would be inlet, and so I might. This is the only small, this is a small adjustment I'm going to change when I'm re-recording this, but technically this thing is kind of reversible. It's kind of a symmetrical part. It's still going to drive as long as I put the drive shafts on the right way. Yeah, I might adjust my other model so that I do it like this. I think this is gonna be smarter. So the back is the inlet end, and what I want to just briefly show from the manual here is I'm just going to look for a visual here. I don't know if they show a very good picture. What I'm looking for is like a screw in a housing here. They show, now they show the exploded view, but I just wanted to take a quick look. I don't think they show a great visual of this. I'm gonna go down now way low here. show kind of how ours are discharging. This is kind of helpful. So there is there's a screw in here. We can't see it. And this is similar to our discharge and it's similar to our inlet, a little bit different. But what we have going on here is on a the way I put my flights on this are going to be one end, they're going to be pretty close to right flush with the end of my center pipe. Like it's going to be generally the inlet end of your screw. We're gonna try to catch everything that's dumping in and then let it start conveying forward from that inlet. And so I really want flights like clear to the end of my center pipe on the inlet end. And some places will even want it even closer than our standard showed us as a 1 inch away. Sometimes they might want even that center pipe to be like within a half inch of the end plate or even closer. I just have to be careful that if I have a bearing failure, this screw can like push into one of my end plates and start grinding away at the end. Anyway, so that's one reason why the standard we're following, a 1 inch away is like ways away from the end plate. But I still want to bring my flights clear as close to that end plate as I can, because otherwise, when things are dumping into the inlet, the further your flight is away from the end plate, stuff can pack into the end plate and before it starts conveying forward. And so mine is whole potatoes. So, 1 inch that I'm away is, most potatoes wouldn't fall through that little 1 inch gap that you're gonna see that when we put the assembly together. But anyway, so just inlet ends in general of these screw conveyors are going to be, my flights are pretty much as close to the end plate as I can get without rubbing and maybe following a standard like I am. Towards the discharge, it's completely different because it depends on where my discharge is. And in this case, mine is like a gravity fed discharge. As the product is conveyed through it, it just falls into the discharge. And so the rule here, and it's probably, if I read through this, but I just have it off the top of my head a little bit, is that a good rule of thumb when you have a discharge gravity fed like we do, um, I'm going to carry my flights about halfway past the discharge opening. So I really want my flights to end somewhere here on the actual screw. So they don't just come to the very edge opening and make the pile push. If they did, that would make the pile have to push the stuff through the discharge. And really what we want is the screw to kind of convey it and pull it in. And so the rule of thumb is maybe whatever discharge opening you have, if it's gravity fed style like ours is, let's go ahead and bring those screws to at least halfway, and definitely not all the way because I don't need it. And in this case, in our situation, uh, if my discharge like this is away from the end plate, sometimes I have to put like the opposite hand of lights on my shaft and auger stuff back to the discharge when my discharge is maybe somewhere down the length of the conveyors. So I may have opposite the left hand flights up here helping anything that got conveyed past and didn't actually fall off. They were actually almost like they were going to carry into the end plate. Well, then that other flight set is going to bring them back and let them drop. So ours is like this, clear to the end plate. So I'm just going to bring in my flights till they end about halfway here. And it's not a real precise thing, just as long as it's about halfway. I think when we did ours in class, we ended up with something that was like within about 4 inches. It was a little bit more than halfway with the flights as we've designed them. So we'll see how that ends. So I just want to explain that again, and it just bears in how I'm going to constrain this flight on here. So I'm not going to ground and root this thing. That would put it probably somewhere in the middle. In fact, I think I didn't even accept that constraint. So I'll do it again real quick. It's just the z-axis to the z-axis and apply that. And then the next thing I'm going to do, so that keeps it on the axis here, but it can slide this way. And so I'm going to bring it back here we did ours in class to the front. I'm just going to think a little bit deeper. I'm going to say actually the inlet end is over here on the back. And so here's my back. Point this like this. So what I really want to do is bring this flight flush to the end right here and just constrain it there. So I think we ended up in class kind of looking at this from several angles and deciding, if I'm looking top down here, just put to my top view. I just want to put this so that the long, the part that's kind of twisted here, that's pretty normal. That's kind of how it will happen when it gets pressed. Maybe the longest part of that, I'm going to I'm going to make it flush to the end here. And so I think we have, let me see what planes we have here. This plane, this plane. It makes this a little bit trickier because the plane that I used is right here, and it's not truly like flush to the end of my flight. It kind of passes through this plane right here if I toggle it on. See the flight actually kind of warps and twists outside of that a little bit. And so that's okay. And really that is like 10 inches from the end. I'm gonna show you how to do this one. Or this two. So measure from that plane to the end, maybe here or something. It's like a 10-inch. It shows a little bit longer than that because of the twisting of the material, but it is a 10-inch pitch. So I'm going to actually constrain it from this plane. Constrain from this plane on the end here to this surface right here. That's my second selection. But I'm going to do it 10 inches. And I actually need it to go -10, but based off my selection choices there. Let's just is driving that from its plane, origin plane, from my surface of my center pipe 10 inches. And then what we did is I went ahead and said okay, or apply that. I'll say okay. And what we notice is looking, and this is something I would pay attention to as well, is my flights past this, and we ended up putting ours right nice and flush. There is a reason for maybe I use my flight and go past my center pipe a little bit and actually constrain this maybe a half an inch this way. And then it would act as that little, it would pick up some of that gap we have between our end plates and the start of our auger on the inlet end, which can help finer product, something smaller than an inch, not pass through here. And I could catch it and then bring it forward in the conveyor. It's an abstract concept when I'm looking at this, but you'll see it in the housing and I'll talk about it again. So but for right now, I'm just going to say, oh, let's just see what the longest part is out here. I think we determined it was this top corner. So I'm just going to measure this real quick from the face flush here to this top corner is this 0.67 inches. So I'm just going to add that to my offset. 0.67, I think I've remember that. So I want to constrain it 10 inches, but then that's a little bit too far. So I'm actually going to subtract that 0.067 from that. And then I'll hit enter. And that actually put the, if I look top down now, that puts it so there's one more constraint I can do because this thing can still spin. It can't move from that. That plane is keeping it there, but that thing will spin around here. So it's hard to tell exactly how true I am there. That's what I'm looking for. The longest flight is to the edge of the center pipe. And I could adjust that if I need to with just that simple constraint. So let's do the last constraint is I'm going to prevent it from spinning on the center pipe. So let's do that. So here's my back, here's my top. I'm going to constrain this at like 12 o'clock here, like this. So I'm going to constrain this plane that's already on my flight part plane, origin plane, the YZ plane. I'm going to constrain that to the plane that's up and down in the assembly, which is the other YZ. Let me do just a plane to plane constraint like this. I pushed it around. Maybe I'll flip it this way. Okay, so I'd use the other solution. Now I've got the seams essentially at 12 o'clock like this. Not that they couldn't be at 6. And if I designed the part that way, it wouldn't have mattered either. So it's just, I'm just considering like, okay, I'm going to put my seams at 12 o'clock. I'm going to say okay on that. Now this thing is constrained. I can see that I've got my tolerance gap kind of built into my part because that would be a size on size and it's this like spirally size. So that having a little bit of tolerance that helps them slip this on. And then these become welded. And I think I talked briefly, when they weld these along, but let's before I talk about that, let's go in and then I'm just going to do a pattern of these. So I just placed one that I'm on my assemble tab. Let's do a pattern of this component. And I'm going to do a rectangle pattern with no rows, just columns. I think I'll just pick the column. And I want the column. I'm just going to use the Z axis. That's how I'm going to pattern this down. This center pipe is with the column being the Z axis, slip work axis, Z. And so it already throws the second one in because the default is two of them at 2 inches apart. But in actuality, I just want the end of this to match the end of here. So it's like a pitch away. If I just change this to 10, sorry, this one to 10, we'll push that one into alignment with the previous one like this. And then we determined, I think we did 9 of these. And that didn't go to the end because I don't want it to go all the way to the end of my discharge. I just want it to go halfway across my discharge opening. So I may have to come and modify this later. And I could modify it on the assembly because the reality is I'm not going to, like, I could take the effort to go in and make a part that was just a partial flight. Just wouldn't be a full pitch. It would be however far this needs to go to be halfway in. It's pretty common in flight manufacturing that the fabricators like to have like an extra flight even. Or if I have this kind of scenario, they'd be like, just leave, give me a whole one. They maybe it's for one reason is flights press easier when they're like a whole pattern, and then they can trim them to fit. And so you do end up with some sacrificial stuff at the end that might get cut off and thrown away. But it's better to have that than have to press like a short little section of flight. Can be almost impossible in some flight presses and can be hard to manage. So just giving them a full flight or a little more than they need is actually a good thing. And so here we just said 9, and I said, okay. And so then I have that, and this is going to get welded out. All these seams have to be welded together, probably front and back side. These seams where these come together, they're going to weld this to the center pipe, whether they stitch weld it or seal weld it, depends on it's what the processes they're moving. In food, generally most things are sealed. In in other materials, rocks or whatever, probably not, but maybe just for strength. So, and what I talked about in class is like the welder will set all these up and like tack them in place, and then they'll put this thing on with its end shafts on a turning machine of sorts, and they can actually turn this flight and then just start welding and just keep walking as they walk along here. As this thing turns for them, they can actually perform this weld as it just spins for them. They can set the speed to kind of match their welding speed, and they can weld all these out pretty continuously without stopping. That does add a lot of heat input to this. There is distortion and shrinkage that happens. People that build flights a lot keep pretty good like records and journals, engineering notebooks, ding ding ding, that if I have to weld both sides of this flight plus all these vertical seams, generally this whole assembly is going to is going to shrink. And so I can end up losing like overall linear length of overall length after I do all this welding on this thing. And so companies will keep a record of like, what these pipe sizes were, you know, the welding process that was used, and they'll take pre-measurements and post-measurements and determine how much distortion they've had in this or shrinkage they've had, and they can add that back in like the next time they do it. Hopefully they, it generally takes somebody some experimentation on that. And so um there are some parameters I think in Inventor that we could run this through to kind of check some of that distortion and shrinkage. If I could tell Inventor how I'm welding it in a weldament, and I bet you I could figure out in Inventor how to calculate that. I could be wrong, but I wouldn't be surprised if that's already a function of Inventor to help just kind of pre-engineer that shrinkage into it. And it could be a half inch, or it could be 3/4 of an inch that I actually lose once all these welds are done. And then I'm way far off my end plates, and I've got, it's in some cases, an unusable part, especially if I've designed the end shafts to fit the bearings just right, and then I've got this distorted part. So it is something these are trickier to build than they look. They look very simple actually, but I would just say there's some engineering notebooks behind these and dialogue, just keeping a logbook of what is going on. Um, and so it's like that magic numbers that they know by experience, that tribal knowledge that those baby boomers are holding on to. So it's there. Okay. Enough talk about this. This thing is I need to save it. So I think I saved this as my next assembly. I think it was 001 for me was the next one I had actually made. So I'm just going to make it 001-1 so I can keep track of it myself. This is just me because of my making the same part twice. Lovely video. How many times have I messed up a video this year? Too many times. That's all right. And then what we did is Yeah, actually, I think I just threw this in the assembly next, right? So what I did is I actually made one more new assembly because I have this assembly, and I could throw that auger into this, but I'm going to call this my housing assembly. And I think pretty soon we're going to send this to production even before we finish the rest, and it will come back with some revisions, um, and we'll go through that process a little bit. But I'm going to make one more master assembly that this one goes into, and then actually my auger goes into. And so I'm really thinking about this next assembly I'm building as being kind of the master assembly where everything will get assembled. And I consider this a sub-assembly now at this point. This housing is a sub-assembly. And so I'm going to make one more new assembly. So just another standard assembly, create it. And I'm going to place in that housing sub-assembly right now. And I'll ground and root it. So I'm bringing in my housing assembly, and I'm going to go ahead and drop one of those in, and I'm just going to ground and root that thing. It's going to be what I build off of. Ground and root that. Okay. Okay. I'm going to be using some of this origin Z-axis in this assembly as well. Yes. So I'm going to bring in my auger part now, my screw here. So let's bring it in. It is this one here that I just built in the video. This was the other one was this one. Actually, maybe like how I built this one better, but let's say, okay, open this one up, place that in there, and now we just need to constrain that in there. So I'm not going to ground and root this one. I wouldn't get it to, I kind of want to experiment with the functionality of it a little bit. So um, I'm going to do specific constraints to this. So I do want to know, uh, I've been, right, let's see, I just need to constrain this in. So I'm going to do that Z axis constraint here. I've got that one ground and rooted. Let's go ahead and do, yeah, that constraints. So I'm going to use the same Z axis in the assembly to the uh, Z axis in, yeah, this is the sub assembly. I'm going to use the Z axis in the sub assembly. It's right there in the part. So it's not one of the parts in that assembly either. It's actually the Z axis for the sub assembly. I'm going to align those two. And that is correct. This is my back of my conveyor. Now that's actually the back, the inlet side of my auger. That's the way I want that to be. Obviously, if it was the wrong way, I could switch it around. But this is the discharge end of my screw, and so that is going to be that's the orientation that I wanted in. So I'll apply that constraint, and then according to our book here and the way we've designed this is to be a 1 inch away. The chart actually said 1 1/4 inches from the outside to the end of this shaft. And of course, mine's 1/4 inch plate. So I'm just going to put a constraint in here that says from this face of my end plate, the inside face of the end plate, to I'm going to kind of look through the hole because I can see it. This is the face of the center pipe. So I'm going to put those flush together, but I actually want an inch gap. That's how we've designed it, is to be that far away, an inch away. So I'm going to apply that constraint. And I think that's the last one I'm going to, so there's only two constraints holding this. I'm sliding down the x-axis, and then I'm holding it on the z-axis. Sorry, sliding down. I'm holding it so I can't pull away from that, but I can still turn it. And this is going to actually show you what I didn't show in class is that I, I can drive this just like we did on our V twin piston. I can drive this and make it go around, and we can kind of show how kind of get a visual on how what the flights look like as they turn, and how you can almost see when you do that, you can kind of visualize how the product is conveyed down here, and based off the direction you're rotating. Because if you rotate it one way, it'll bring it towards this end. If you rotate it the other way, it will bring it away from this end. So, technically my right hand flights can do both. Depends on where I want to go and where I'm coming from. But So I'll do that, but I think the last thing we did is we jumped in and did kind of the what I'd say is the driven end here shaft that goes inside here. So I'll add that onto my video here. So I've got this constrained. I've got it ready to drive. If you remember, well, maybe I'll talk about that real quick before we left. How we did it on our V twin piston, we can kind of use that same method here. What we did was I might position this, kind of get it ready. So top is top there, and then I designed these with this in mind to be like 12 o'clock. But what I'm going to do is just do like a plane, like an angled constraint to a plane. And so if I look at my, maybe, so this is my subassembly for the screw. Here's the planes in the subassembly. So if I look at this YZ plane right here, slightly it's not perfectly up and down because I've just rotated it somewhat, but that's the YZ plane of the screw. And if I actually do a constraint, an angled constraint to the YZ plane of the actual this assembly, like this is kind of how we drove that other one. We made these as like 0 degrees and snap them together like that. We've got like a angled plane to plane alignment. I think this will work. I think I could choose either of these. This might flip around. Maybe that's okay too if I choose a solution. It's okay. So now it can't turn, but I can drive that turn. So it would be like come down to this angle constraint that I just applied and go ahead and right click it and say drive it. The way we drove our twin screw, V twin piston, sorry, or V twin piston. And the same way we're gonna drive this is I'm gonna go from 0 degrees to 360 degrees. And then we expanded this out here. And maybe I'll just do like 10 of these, like 10 repetitions. And if I go ahead and hit play here, so this thing is turning this direction. If I'm looking at this way, it's a counterclockwise dimension. Really, my drive is on this end. It'll have a shaft sticking through here. So I'm actually from this end, I'm spinning clockwise, and that would dump product in, and then it would convey down along here, like where my cursor is following these. If I spin it the other direction and I dumped product in here, it would start to convey it into my end plate and it wouldn't be able to discharge. It would pile up and make a mess, break things. Um, and simple rotation can be corrected by whoever installs the gearbox and motor, and generally the way they wire the motor can actually turn that the way. So sometimes when you see new equipment installed, here comes the electrician, they just wire it up, and they say, hey, bump start that. And then somebody bump starts it and they're like, oh, that's turned the wrong way. And they just take it off and switch 2 wires. And then it takes off the other direction. So yeah, you see that a lot when electricians are kind of troubleshooting. They've got things, usually they'll want usually, well, they can probably make sense out of it. A lot of electricians have a lot of experience, but some of them might have you there and say, is that spinning the right direction? And you're like, yep, it is. Because it would be this direction. Counterclockwise from this end or clockwise from the other. So that's going to move product through there. That's cool. Let's build an end shaft for that. So I'll just pause and stop that real quick, jump out. Just driving that angle. So I didn't do that in class, but there's a free video here. And then, yeah, I'm going to save this one. So what I did is after I had done this stuff, I saved it as my next assembly, which was 102 for me. Yeah, 102. Sorry, -1. So these are all my copies of mine. Okay. And then what we did is we made one more part. So I'm going to go out and make a new, just a standard part here. So standard part. I'm not going to do a sheet metal part. I'm going to make the driven shaft. So, and then what we did is I derived in. So I'm going to do a derive here. The actual center pipe. I'm going to kind of design around the center pipe here. So let me find it. Should be my 716-1 is my center pipe for this one. Yep. So I'm going to bring this in. I just want a surface to come in. I'm not going to toggle anything else on, just a simple derived part. There it is. It should come in with front as being discharge and back as being inlet. So I'm going to go ahead and design from this end to the back edge of the inlet end where the driven shaft is. And so what I'm going to do is look at my manual one more time. And I'm going to look for those I think they're up above all this. Just below the flights is where this shows up. Particular some variables I'm looking for. Am I wrong? I'm sorry, I said it was below the flights. Then I'm kind of getting spaced out. Let's see. Not that one. The one that has, I probably went past it, just didn't even, right there. This one's, it's got my variables. They might not be correct for the materials I'm going to use, but they'll be a good starting point for this. So I'm planning on adjusting this. I'm just trying to get a feel for what these, what these dimensions are, and I'll change them as I need them because it's, what we've got. I think we determined in class. Really, I need, so what's going on is I'm going to make this out of solid bar and I'm going to insert it into the center pipe and then we're going to pin it together. Sometimes they will insert those together, drill down through the whole assembly and then bolt them together. And that's okay, but it puts a bolt and some hardware on the inside of a piece of equipment, which in a food processing plant, they don't love that. They minimize that as much as they can. So another option they have is to do the same drilling process. Then they actually put a solid bar down through there and then plug weld the ends. And that kind of traps and locks these together. And it is not as easy as removable as bolt-on hardware, but it is removable. I can actually see where the pin is located and just essentially drill out the welding and then actually knock the pin out. And so it's a little bit more of it seems like a permanent setup, but it actually is still maintenance, still able to change out. I mean, because it is made to disassemble and potentially rebuild as components fail. We kind of are building a rebuildable sub-assemblies here, and even if they're pinned and welded together, they're still disassemblable. So not as easy as a bolt, but technicians have skills that can do it, and so we've got to think about, and that's what's going on here. They're actually showing hidden lines of so they've actually drilled through everything right here, through the center pipe, through the solid shaft. There's just a hole all the way through it to pin it together or bolt it together. And they've actually then done a second hole, like 90 degrees from the first hole. That's why I have like a hidden line shown here. That's actually where the next fastener would drop through. It doesn't really show it accurately because it should be all the way through the through the solid shaft and then through the walls of the pipe. And so it's actually drilled all the way through, and then it's off a certain distance away from the very end of that. But this is specific how far I want to insert this into the pipe. Like I don't want to go like clear far in there, but if I hold it, I'm going to hold it to kind of their standard, at least right here, that they say that B dimension is 12 inches overall. So the shaft, I'm just going to make it 12 inches long. I mean, there's some other weird details going on here, but don't worry about it. I'm just going to make it 12 inches long. And then I'm going to, then I'm going to insert that thing. And so this is a 2-inch diameter, by the way. It's 2-inch diameter is what they're telling me. And we'll talk about that. We may adjust this, but initially off my chart, it says it's 2-inch diameter, needs to be 12 inches long. And then the C dimension is how far from the edge of my center pipe, how far it comes out. And their C dimension is 7¼ So I think we determined that this is like 7¼ and then this is or 12 minus 7¼ is how far this is. So I think we determined this is not drawn proportional. It's actually longer in the C direction than it is from the end of C to B. So because it's just the overall thing is 12 inches and 7¾ are sticking out the end of the center pipe. 7¼ point difference. So 4¾ is essentially from where C ends to the end of B here. So I'm going to think of these dimensions. I'm going to go in dimension and just quickly on that derived part that I just did, I'm going to draw that out. So I'm going to come in here and I'm on the back side where this is the driven side. I'm always going to say that backwards. This is the driven side, the side I was just looking at on my conveyor. And I'm going to do a sketch here. So I'm going to start a 2D sketch, get away from that 3D sketch. I'm going to use this back face of that center pipe as my sketch face right there. And that's really where that shaft is going to insert here and transition from, carrying the flights across the housing. Now I'm transitioning through the end plate and I'm going into a bearing. And that's what's going to happen here. And that's what this drive shaft, it's a machined part. something that have to be really accurate in how. So when we get to our machining prints for things that are going to be machined, we're gonna up our level of accuracy and maybe apply some GD&T here. So we're gonna have to do some controls here that we want our machinists to really pay attention to. And so this is the start of that process. This particular shaft, I mean, that's just a chunk of pipe. This particular shaft is a machined part with some other details we've got to add. But what it is going to look like is just a circle. I'm going to lock into the same origin point here. And it is a 2-inch shaft according to my chart. So it's just a solid shaft like this. You can see already it has clearance on a 2-inch standard pipe. And so we can talk about, I didn't discuss too much yet, but I do have this issue where like, is that like too sloppy to fit in there? You know, is it just too much tolerance to insert this? You know, because if it is, it'll be hard to like get this perfectly straight to the pipe being straight. And that's what I'm trying to build is this nice straight shaft essentially to drive my flights. And so this may not be, you know, sourcing 2-inch material might be insufficient to do this on standard 2-inch pipe. So we'll come back to this and think about it. I'm going to keep it at 2 right now, but just having that visual of what's going on, you know, this space between the inside of the pipe and that, I need to consider what that is, and maybe consider a thicker pipe or consider a larger diameter rod to start with and have my machinists whittle their way down to something that will fit in here. And so, but we'll talk about what we've got going on there. Right now, I'm just going to say it's 2 inches, and I'm going to finish that sketch, and then I'm just going to offset it, do an extrusion that's asymmetrical. And so I'm going to see the part that goes inside and the part that goes outside. The part that goes outside, they have them, you know, different sizes here. Distance A on mine. Well, that's 7 1/4. And then the part that goes inside, because the overall thing was 12, so this was 4.4 3/4. So that's my 12-inch part, driven shaft, with kind of how they're calling it out. And then I just need to do some checks and do some more figuring here. So I'm going to say okay on this and define this as stainless steel as well. And it's going to be semi-polished. And then I think I didn't really define the description of this yet because I'm just not determined that's what this is. So I did save it. So it's my next part in sequence. So I think I called it 18. So I'll call my new one 18.1 for this assembly, save it. And then I saved that. And then I went and I inserted it into my new kind of master assembly. No, I didn't. I inserted it back at the this assembly, the sub-assembly for the auger for the screw here. And so this one I should be able to ground and root. I don't think I did it before. Maybe I did. So I'm going to bring in that part that I just made, 18.1. Go ahead and place that in here. Looks like a lightsaber, right? I think I said that. So then we're going to, I'm just going to ground and root that one here now. So if I ground and root this as designed this way, it does apply it to where I designed it to be, right? It's on the back side. That's the driven side and the inlet side. And so I've kind of designed, I think I may have done something different when we did this in class, but I did think about that a little bit more, like where I built this part from. It might have been how I put my flights on the actual shaft that I messed up on in class. It's not a huge mess up, but I'll probably make some people fix it. But it's actually, it wasn't a huge problem. I just caught it this time around, actually. And so now when I go to this assembly, which is my new master assembly, that part should show up. I'll update it. There's my part. This one has my driven angle that I can go ahead and drive, I think. 360. Did I do like 10 of them? Like, play it. Yeah. So that's just as far as we got. I'm gonna wait for this to come around. Talk about left and right one more time. Stop it right there. So this is like I would come to the end of that. If I couldn't recognize, is this left or right hand thread? I do this like come to the end where there's this cut in the augers, and I say from here, If I look down on this, this goes down and to the right. This is a right-hand thread, right-hand flight. I'm sorry. And then if I go, if from this point, kind of where I can envision a scene here at 12 o'clock, it goes down and to the left. That's a left-hand threaded flight. So it's kind of usually how they'll identify those. Um, and then determining which way it needs to spin. Well, that's depends on which way I motor, I wired up and the way I've designed it to either be driven from one end or the other. And I've designed mine to be driven from the discharge end. So pulling this stuff through. All right. So I'm happy with this. This is the end of my video. I think it was quite a bit shorter. Um, and we'll pick up from here. Yeah, this is what I'm kind of looking at is when this is in here and I'm dumping product in here. This is where it could potentially pack in here because it's not going to really, it's got to catch this flight and then start conveying down and away. Um, so small potatoes right now, I get to like drop in here, maybe not catch the flight as they come across. So I could get some packing of material. If it was a powdery material, I don't think this would be a great application for a real powdery material. I would end up with a lot of residual product just sitting here waiting to be conveyed. And it's going to sit there and rot away. And then eventually it's going to trickle out and be conveyed with fresh product. So it's just something. Well, and so what we could do to address that is like what I was talking about. And I'll stop this one more time here where it looks like that. This is where sometimes they will make these flights where I'm going to design my center pipe to be this far away, but I'm actually going to put my first flight on a little bit further than past center pipe and have it hanging out here, almost just kind of like floating in the breeze here a little bit. But help it to span this gap. I have to still stay away from this. I don't want this to run. And so I could like design the center pipe as we have and drive and everything, and then bring my first flight further on and maybe come away from this 3/8 of an inch, half inch. But I could kind of fill some of that void and catch some of that material. I've also seen them put on almost like a squeegee on here that kind of would bolt in and be like a plastic that would be that I could even get closer. The reason why I might use plastic is just I still don't want it to rub on my end plates, but it would be better if that rubbed my end plate than metal on metal. And so, that would be kind of a wear piece that as a maintenance tech I'd be looking for and saying, is that thing rubbing on that yet? Oh, and then I would know that my screw had traveled in the housing somehow. And so these are visual things that I would look for as it's operating to make sure it's operating right. But I could put almost a little squeegee on here that was even catching the material that was kind of tending to fall behind the flight. So yeah, there are some design considerations here that I would have to really dive into, and but I don't need to yet. I just wanted to kind of show you that is, you know, this being this far away may not be the best for some products, and even some of my potatoes can end up being like caught here. Another consideration I didn't talk about in class was depending on how thin mine's 10 gauge here. This is 10 gauge thick. That can become pretty sharp over time and kind of wear to almost a knife edge. You will see sometimes on the inlet ends of whole product that they want to protect. If I'm conveying whole potato, I'm trying to protect it the best I can. And I don't want it to get sliced a bunch dropping onto this. And so they will take and put a piece of round rod and follow the same flight path and form some round rod into like a solid round bar into kind of that helical curve shape. And then they will tack weld it on the edge of this, I've called these raw edges of sheet metal, and they are kind of sharp. And so you could protect the product with a rod on the edge of this actually. So of course I have to be careful. Does it rub my housing if I put that on? I've got a half-inch clearance all the way around. So, can I put a 1/4 inch rod on here? And would that help like not cut potato as it drops on? So these are design considerations as things get designed and then they get put into operation. We realize there's some things we missed and we come back later and we say, that should have had this or that, and screw conveyor manufacturers, they've already taken some of that into consideration. You might not see it in a manual, but you would see it at their facility saying, this is what we do here, this is what we do here to prevent kind of stuff like this. We have different tolerances we use because of the product we convey. So this 1 inch gap is going to be no good. And so anyway, there's just things that we change based off experience. So I'm going to say that is the end of this. Catch you guys next time.